A term that may not have been completely defined is the lithosphere. The lithosphere is the crust of the Earth and the uppermost part of the mantle layer beneath. It is in the lithosphere that tectonic activity occurs. At some point deep in Earth history, the atmosphere and oceans formed, and as a result, sediments have been accumulating. These sediments and the rocks they produce will be the subject of this lesson. Sedimentary rocks include limestones, sandstones, shales, coal, rock salt, and conglomerates. And the varied systems that generate each type are incredibly complex, so we will give it our best effort. The biggest influence is the tectonic setting. Our book uses tectonics to refer to deformation, or in other words, destruction, or structural activity over a widespread area of the lithosphere over a long period of time. Areas like the flat US Midwest are not very tectonically active, whereas areas like the US in its western regions are very tectonically active. That's why earthquakes, mountains, and volcanoes are a thing out there, more so than around this part of the country. Where plate tectonics occur on the surface of the continents, mountains typically form, and the mountain is largely where the breakdown and transport, or erosion, begins. The sediments that get deposited at the foot of the mountain are in larger pieces, and the further you get from the source rock, the smaller those pieces tend to get. The low places that the sediment gets deposited into are called depositional basins, and in places where these basins are sinking or subsiding, more and more sediments get laid down until great thicknesses are achieved. If you haven't already guessed, this chapter is full of fancy sounding words. So here are some more for good measure. On a continent, the interior stable portion is called a craton, which can be broken down into shields and platforms. And the other tectonic component is called an orogenic belt. The craton components are not tectonically active, and the orogenic belts are very tectonically being lifted up into tall mountains. The shields are made of crystallized rocks exposed on the surface, and the platforms are areas where sediments are burying the shield. So the important aspects of this lesson will be reverse engineering the sedimentary rocks in order to establish what the physical, chemical, and biological factors are that led to their formation. There are a ton of depositional environments, but our class will focus on the big three: marine, terrestrial, and transitional. First, let's talk about marine depositional environments, which typically form in shallow ocean waters on the top of the continental shelf, which hopefully can be remembered by the fact that it looks like a literal shelf. Sunlight is able to penetrate the water in these areas, which is necessary for the type of life that produces the limestone sediments. Moving further out to sea, we have the continental slopes. In order to get to the slope, sediments are usually caught up in turbidity currents. Please watch the turbidity current video in the Lesson 5 D2L module. The only sediments that make it into deep waters are very fine. Now we move on to continental or terrestrial deposits. Our first example is stream, otherwise known as fluvial deposits, which can leave alluvial fan deposits when fast-moving water dumps the sediments onto the foot of a mountain. Lake deposits are known as lacustrine deposits, which is where gentle waters surrounded by land deposits silt and clay, very fine and small particled sediments. Huge blocks of terrestrial ice, known as glaciers, are one of the few forces powerful enough to move huge boulders across miles and miles. The exact opposite is wind deposits, which only have the energy to transport the smallest of sediments. Now we have transitional environments. These are pretty much exclusively on the coastlines of the continents, and over time, as the sea levels rise and fall for various reasons, These transitional deposits switch from the more inland shales and sandstones to the limestones of the continental shelf. From inland to seaward, we observe deltas, barrier islands, lagoons, tidal flats, and estuaries. Deltas and estuaries are only slightly different, so I'll explain. Deltas are where a stream and/or river deposits its sediments into quiet lake or ocean waters. Estuaries are where the fresh waters meet the salt waters of the ocean. In estuaries, the sediments can be sand in powerful tide conditions or silt and clay where the tides cannot reach. The color of sedimentary rocks can tell us about the amount of organic matter or black carbon was present and whether it was exposed to oxygen. See, oxygen in sediments supports the life that breaks down organic material. When this happens, it turns to a more red color, like rusty metal. The texture, size, and sorting of the grains in sedimentary rocks tells us about the journey those sediments took to become rocks. We discussed rounding in the last video, so we'll skip to sorting. For example, carbonates deposit smaller particles in quieter water because high-energy water traps those smaller particles in the water. Also, fossil shells are more intact when deposited in quieter water, whereas higher energy water tends to damage and break and fragment the fossils. Overall, the further the sediment is transported, the more consistently sized the sediment particles are. Near the mountainous source of sediments, the grains are deposited at once because the stream waters slow down suddenly. Further away, the stream waters don't slow down as quickly. So the sediments are deposited just a little bit at a time, from the largest grains to the smallest grains. Now the sedimentary rocks contain a lot of features that takes years of training to recognize. Features like mud cracks, which indicate drying clay sediments, cross-bedding and ripple marks, which indicate sediments moving in the same direction by wind or water, or graded bedding, which indicates which direction is closer to the surface when they were originally deposited, are all present in sedimentary rocks. Also, by matching the exact mineral composition of a sandstone with potential source rocks helps us track the journey of the sand sediments. Now, we aren't identifying rocks in this class, so we are just going to skip right on past this stuff. And I think we've covered limestones pretty well between this and the previous lesson. Professional geologists worked out a system of connecting sedimentary rocks to the depositional environments they represent, called facies. For transitional environments, this results in our understanding of past sea level change. Since the distance from the shores determines what types of sediments is laid down, it should match our expectation that if sea level changes, then the deposits move in lateral zigzags. This is one of those things that has been repeatedly tested, confirmed, and named Walter's Law. Sea levels can drop when the climate gets cooler, because the Earth's finite water gets trapped under ice. Trapped in the glaciers. This water gets dumped back into the oceans during warmer times of Earth history, which leads to higher sea levels. Unconformities are an important topic, so I'm assigning a video about them from the Geoscience Videos YouTube channel. We won't be asking you to make stratigraphic cross-sections, but it is important that with progressive effort and mapping of layered rocks, historical geologists continue filling in the gaps of Earth history.